Even though most physics books split these things into two chapters, interference and diffraction are really the same thing. The basic idea is light spreads out and we can't confine it to a small region without increasing how much it spreads when it gets out of that region. Huygens' principle will be very valuable here. We kind of know instinctively that something like this must happen if we imagine a breakwater constructed of logs or piers or something like that in the ocean, and we have a line of water waves hitting that breakwater. We don't expect these tiny little squared off waves to come out of it. What actually happens is these openings act like spherical radiators, as this picture in your book shows. This spread of water going through the obstruction is diffraction. You can see this for yourself if you hold your hand up to a light and look at the tiny gaps between your fingers. You'll see bands of light and dark caused by diffraction, and this happens because the gaps in your fingers are not huge on the scale of the wavelength of light. This is also why you can hear people around a corner or out in the hall through a doorway, because the wavelength of sound for speech is in the tens of centimeters to about a meter ballpark, and that's also the approximate size of the doorway. We can hear around corners, but we can't see around them because 1 meter is much, much larger than the wavelength of light. The result of spreading when we go through a small slit looks a lot like what we saw when we looked at double slit interference patterns. We can understand this if we apply the same reasoning to the slit by imagining instead of being a physical slit of width d, it's really two slits of width d over 2 right on top of each other, right next to each other. If we have those two slits d over 2 in size, we recognize that the top of the top slit and the top of the bottom slit are d over 2 apart, and in fact every single point along the top slit has a matching partner on the bottom slit d over 2 away. We can use this to find points where destructive interference occurs because we know if our path difference between these two made-up slits is d over 2 sine theta, we'll get dark spots whenever that equals half a wavelength. We can manipulate this algebraically and say, okay, if d sine theta equals lambda, we get a dark spot. From there, we can imagine breaking this into 4 adjacent slits, each d over 4 long. Then we'd have d over 4 sine theta equals lambda over 2, and we'd get cancellation there. And again, each point in a slit has a partner in an adjacent slit to cancel it out this way. This gives us d sine theta equals 2 lambda. Why did we skip 3? Because in that case, each point in a slit will not have a partner. We'll have something left over and we won't get cancellation, we won't get a dark spot. We have to have an even number of subslits, so we go next to 6 slits of length d over 6. If d over 6 sine theta is lambda over 2, that gives us d sine theta is 3 lambda. We can figure out here the pattern is pretty obviously d sine theta equals m lambda to find the dark spots. Why then are the bright spots not at the halfway points between these? The reason is the underlying function is a little more complicated. Your book works through a derivation, but our main idea is if we define a function beta that depends on d lambda and theta as pi d sine theta over lambda, we can then write the brightness as the sine of this beta divided by beta squared. We look at the way this function changes as the relationship between d and lambda changes, because this only depends on the ratio of the two. We don't have to change each one individually. We can just change one to change the ratio, and that'll tell us everything we can learn about it. The range for theta, if you think about the limits, it could be, if we had an infinitely long screen, it could be all the way down to negative pi over 2, all the way up to pi over 2. So that's the full possible range for an infinitely tall screen. If our slit is just 2 lambda in size, this is what our screen would look like. We'd have a bright spot at the center, then it would get darker at the edges, another bright spot that's not nearly as bright, and then darker again. And notice these are at very large angles. On the other hand, if we have a wider slit, we get the same idea but less spreading. Notice that I've reduced the range here. Now instead of being from negative 90 to positive 90, we're more like negative 60 to positive 60. And as far as where we can actually see some light, then we'd be cut down to about plus or minus 30 degrees. If we go to 100 lambda, now Here, this range is, the whole thing is only about 5 degrees on either side of the center, and we're again only using about half of that. So this is a couple of degrees either side. The larger the opening compared to lambda, the smaller the amount of spreading. That's the big deal. This is what you should have seen in your house if you've ever opened the curtain in front of a window facing the sun and then you look at the wall opposite the window. You see a bright image of the window on the wall, and it's pretty much the same size as the window. It doesn't spread out and you don't have dark spots around it. And the reason is the window width is very large compared to lambda. This is really something we should have considered when we looked at double slit interference. There we just talked about the interference part, which would give us this purple sine wave here that the intensity never drops. The diffraction would give us this large bump here, and in reality we have both of them together, which gives us the red line. If there are a lot of slits, you get what's called a diffraction grating, and the key feature is it acts like a prism. It can split light into its component wavelengths and can be made much more cheaply than even a hunk of glass like a prism. One example of this is a CD or DVD where the tiny grooves act as a diffraction grating, and that lets you point the DVD at the sun, and you can throw reflected rainbows all around with that.